Have you ever wondered where this trig identity comes from? If you know a little bit of linear algebra or differential equations, I'm going to give you two different proofs today. The first one was right behind me, but let's go back a step before we get there. If you've taken linear algebra, you know that there are certain transformations of the plane like rotation or reflection or stretching that can be encoded using matrices. For instance, if we rotate by any angle, we just fill in that angle here with cosine, sine, negative sine, and then cosine. So for instance, I have three matrices here, and they're encoding rotation by x plus y, rotation by x, and rotation by y. Now common sense says that if I first rotate by y, and then I rotate by x, that's the same as a total rotation of x plus y. So that should mean that if I compose these operations, remember in math we work from right to left when we compose functions, that operating by this one and then this one is the same as the blue one up there. But that should mean if we literally multiply these matrices out using matrix multiplication, then the purple entry should match the purple entry and the blue entry should match the blue entry. And one of those is the trig identity we started with. This is really cool, and it's actually my favorite proof of what's going on with these identities. It's actually the same proof that you may have seen using polar coordinates and complex numbers. And maybe I'll let some people put that in the comments because that's another beautiful proof. But the next one I want to do actually uses differential equation. If you've taken a differential equations class, you've probably studied this equation. Hey, find me a function where two derivatives gives me the negative of what I started with. And it's not hard to see that sine of x and cosine of x both have that property. You learned that in your first class in calculus. But notice here I've said every solution is of this form, right? It's some constant times sine of x plus some constant times cosine of x. This is actually a lot deeper, and it has to do with the fact that when you solve a degree 2 equation like this, that the solution space forms a two-dimensional vector space. 2 because you have two derivatives. I can make another video if people want to see why that is true, but once we have that, it means that if we have any other solution, like notice sine of x plus 2, take two derivatives, use the chain rule, you see that that's another solution to the original differential equation, so it has to be some constant times sine of x plus some constant times cosine of x. Now, what are those constants? Well, just plug in some values and let's see. And so some convenient values to plug in are maybe 0 and pi over 2. If you plug those in, they immediately tell you what a and b have to be. Down here at the bottom, notice I use the fact that if you take the sine curve and you shift it by pi over 2, you actually get the cosine curve. And all of that is to say that sine of x plus 2 is a times sine of x plus b times cosine of x. And notice we get exactly that trig identity that we got earlier. If you don't like me using the number 2, you could put any constant a in there, and then you would get a formula for sine of x plus a equals